So let's continue in section, let's see, this is 5.3, the definite integral. So we had worked last class really with this idea of finding the limit of Riemann sums. So we're going to explore more of the kind of the shortcuts for evaluating this, because I know this was a lot of fun to go ahead and translate the definite integral to the limit of a Riemann sum, and then go ahead and work through all of this just to take the limit like this. I know that was a lot of fun, but there are some shortcuts. I'll talk about this more review day. I believe you won't have to do this as long as you know the shortcuts. So really kind of focus in, but this is kind of the fundamental principles, the underlying. So we're gonna make sure we understand the connection between this and limits on the next page, and then the rest of the lesson we'll focusing on evaluating using some formulas and understanding it as the area under the curve. Maybe one other thing just to kind of put back in your mind. If you consider this area and this area, we're able to compute this with some geometric formulas. Realize that the answer to this, does anyone remember what the answer to this was without looking at the bottom of the page? It was 16. So it was the positive area, and then we have the negative area that takes away. So maybe just a quick little thought about when would the area be, or when would this take on its maximum value? Well, when the area is always going to be positive. So that's just maybe a little hint for a homework problem that doesn't have a view and example. So let me say that again. When is this value maximized? When all of the area is positive. You'll see that in your homework. All right, so let's go ahead and make sure we understand how to translate any sort of limit to this definite integral. So maybe just to recap, what we were working with last time is the limit as n goes to infinity will help us calculate the definite integral, and the n is just, we're basically considering how many rectangles are. So we're letting there be infinitely many rectangles. And to find the height of the rectangle, you found f of a plus k times b minus a over n. That gives you the height of the rectangles in the certain interval. And then you multiply that by b minus a over n, which is going to give you the width of the rectangles in the certain interval. So this was very specific. That right there was saying all rectangles are of equal width. But another way that maybe a more general statement is to consider the limit as the norm of p goes to 0. Does anyone remember what p stands for? It was back from section 5.2. It is do part of you remember? Partition. Remember that p represents partition. Those vertical bars next to it stand for the norm. Does anyone remember what the norm of a partition is? It's the largest, more specifically, it's the largest width of on the partition. So if we had a simple partition, maybe just for reference, let's say we had a partition that was just like, let's say 0, let's say then we have 0.8, and then we have, let's say 2, let's make this a little farther, let's say 2 over here. The norm of p in this case, does anyone think they know? If it was just partitioned into two pieces, Destiny? Oh, I thought I saw it behind your mouth. Anyone think they know? If that's the partition? Oh God, we're reviewing. So what is this width right here? If this width is 0.8, what is this width right here? 1.2, which of those values is larger? So therefore the norm of that partition is just 1.2. Okay. So again, it's a little bit of a notational thing. Okay, so what we could do, if we let the norm go to 0, that is to say the largest interval becomes arbitrarily small, Then we could go ahead and rewrite what's on the left like so. We still could consider the sum from k equals 1 to infinity of f of c sub k times delta of x sub k, where that is just going to be the height and the width of each individual rectangle, where they're not necessarily uniform. That's why we don't have the same nice formula where we have over there. So anyway, that's a little bit of review, but since these are related, and the only thing is, really when they become so small, we don't even care if they're equal width or not. So what we're going to do is take this right here, and we're going to realize that we could translate that to this. The definite integral from a to b of, let's see, I want to make sure I write this correctly, of f of x sub k, or just say f of x times dx, because it's just going to be a function. And so this we can easily compute using antiderivatives and the fundamental theorem of calculus that we'll learn in the next chapter. Okay, so now that we know the translation, what we're going to be doing in these problems is essentially this arrow. We're starting with this limit, and we're going to write it as a definite integral over this partition. Okay, so what we're going to look at here is this is my A, this is my B. Again, that is just going to be some interval on your x-axis. So we're going to rewrite this. This is a little bit weird to look at because of all the k's. That's basically what we'd iterate through. But this right here, this 2x cubed, or 2 times c sub k cubed, this is telling me that my function is going to be 2 times some input cubed. So that's my function. This right here, let me change my color, the delta x sub k, that right there is just the change in the x values. So it's telling me that my variable is x. So with that, let's go ahead and write this as a definite integral. So our lowest endpoint is 0. Our high endpoint, or our endpoint on the larger one is 0. So -1 to 0, that's a to b. Our function is 2x cubed, and our variable is x. So that is the integral that we're going to be evaluating. And we'll evaluate that more as we go. But that's how you translate any sort of limit into a definite integral. Or a limit of this form, I should say. Any questions where any of that came from? Okay, that was a lot of setup for a fairly simple problem. Yes, I know. So let's go ahead and look at the one down here below. So the function this time is going to be the square root of 4 minus ck squared. And then again, our variable is going to be x. So what we'll do is write this as the integral from a to b, in this case 0 to 1, of the square root of 4 minus x squared dx. That's all. This is kind of the connecting part. Anything else I wanted to say there? So maybe just so the function we're looking at here is the square root of 4 minus x squared. Does anyone think they know what that, the shape of that graph is? Does anyone recall? Does anyone have a semi-idea? Linear. It's not linear. It's a semicircle. Very good, Grace. So this right here is a semicircle of radius 2. So let me go ahead and get me a semicircle up here. So there is the graph of that function. So what is the let me give you a moment to think about this. What is the area, or what is this area going to be equal to? Well, 0 for 1, we're looking at this. So this right here is what the answer would be. So right there is going to be some area. Let's just call this A in there. So that's what this is going to be equal to. To compute that, well, can we do that without actually telling you the integral? Not that one, but maybe a subproblem just to see if you all are following. What if we had from -2 to 2 of the square root of 4 minus x squared dx? Anyone think they know what that answer would be? Just to see if we've caught the idea. I'll give you maybe another 20 seconds to think about it. You think you know it, Chapel? Huh? 20-something? I don't know. I haven't worked it out yet, to be honest. So we have a vote for 20-something. Here's how I would approach it. So if we're looking at the semicircle, what we have in gray would be the total area here, because that we want to go ahead and consider from -2 to 2. So what is the area of this part up here? Well, you could do the whole circle. So the area of the whole circle would have been, let's see, pi r, well, in this case, it would be 2 squared. But for the semicircle, we would have to divide it by 2. So this is going to be pi r, well, in this case, radius 2 squared. But we're going to divide it by 2. So it's just going to be 2 pi. So not quite 20-something, 6.28. So any questions about what this definite integral means? Okay. So let's go ahead and look at this last one. Let me give you a moment. Oh, there's a little typo here. We haven't talked about changing indices. This should be from k equal to 1. Actually, all of these should be k equal to 1 as your bottom index. We haven't worked with changing indices and changing the kind of the limits of the summation. So make that adjustment. That should match whatever we had up here. Okay, so let me give you a couple seconds to try number 4. Just write it as an integral. So once you observed that your function that we're looking at right here is going to be secant of x, and our variable is going to be x, so, oops, little typo there. It should be from your negative pi over, I'll get it right this time, 4 up to 0. How many got it? Just to make sure. Okay, good. I just wanted to make sure the majority are seeing where we're at. What this is equal to, we don't know how to evaluate it yet, but I just want to kind of continue to emphasize, like, what are the answers here? So if you were to graph secant, let me take a moment and give this mine. So the graph of cosine looks like this. So the graph of secant is going to go up like so. And this right here would be pi over 2. So what we're looking at, the actual answer right here, would basically be, let me go ahead and get this region shaded. That region right there under the curve. Technically, I should curve that. Okay, yeah, so close enough. It should be against the curve, but the answer to that definite integral is what the area under that curve would be. So, any questions about any of these questions right here? Okay, so what we're going to want to do is have some properties on how to simplify these definite integrals. So that's what the next page is. Again, I really wanted to emphasize that these represent the area under a curve, so there's some nice properties. Let's just talk through them, and we'll apply a couple of them down below. So these are the rules for definite integrals. They have both geometric and numeric interpretations. The first one is the zero width interval. So if you look at this one right here, if you literally have an interval that's on top of itself from A to A, how much area is there here? None. It is literally closed on itself. So be aware. For example, like if you had, maybe just give something e.g., if you had someone throw out their favorite number, 12 or 127. There we go. We'll merge them. And let's say we had this right here. We don't necessarily know the relationship between the antiderivative and the definite integral yet, but what is that going to be equal to? 0, because again, 127 to 127, we have no width to our interval, so therefore its area is 0. B is the constant multiple rule. So again, this up above is using k specifically 2, but if you have some sort of area and if you multiply the function by 2, you basically just double the area. So in other words, the constants can be brought out in front. We already talked about this rule with the indefinite integral, so it carries over with the definite integral. The third one is a nice one. The sum of the areas. So if you added the blue area and the orange area, you would end up with the green area. And again, technically this green area is all of this down here, including it. But you can see that when we add some function's area to another function's area, we get the same amount of area. So you can break up the integral over a sum. Notice that the a to b are all staying the same. This one is a nice one because this allows you to deal with negative numbers. So let me highlight a few letters. Notice if we considered the integral from a to b and then add that to b to c, we could have shortcutted that by just combining these right here. So just kind of color coding the like intervals. If you have this interval and this interval under the same function, you do not need to calculate them separately. Just write it as one with going from A to C. Instead of going from A to B, then B to C, just go from A to C directly. So that's a nice property. We'll look at an example down below. This next one's a little bit weird to look at. It's a lot of notation. But basically, it just provides bounds for the area. That is to say, this is basically saying let me look at this. So you have the minimum value of a function, and then you have the maximum value of a function. The actual answer has to be somewhere between them. And the last one is just another scenario of kind of working with boundaries. These will show up a lot more in Calculus 2. We'll primarily work with the first 4 here. And this one just is basically saying that if a function is always larger than another function, then the area is going to be greater. To me, it's fairly intuitive if you understand these as area. Okay, so let's go ahead and, there's one more rule not above. If you flip the areas, or if you flip the limits of integration, so if this was from A to B, you could change this going from B to A, but all that's going to do is flip you to the other side of the axis, so it's just going to be a negation. So that's a nice little trick to go ahead and work with the other rules, that if you change this from A to B, to B to A, then just make sure you put a negative in front. All right, look at number 5. Given that the integral from -3 to 2 of f of x dx is equal to 5, and given that the integral from 0 to 2 of the same function, notice here again, same function, f of x is equal to -1, evaluate negative 3 to 0 of f of x dx. So how are we going to approach this? Well, we don't know what f of x is, but we do know what the area would be equal to considering parts of the x-axis. So let's just kind of set this up a little bit. So let's just consider the x-axis here. Here he is, straight as ever. Let's see what we have in each case now. We'll see. Our lowest number here is negative 3. So let's do negative 3, negative 2, negative 1, 0, 1, 2. So that seems to be the parts that we're working with. So this first part is negative 3 to 2. So if we were to consider the entire area right there, that would be 5. Again, I'm not drawing the y dimension because I don't know what the function is, but we do have that information. We know this. We also know, let's go ahead and get another color, 0 to 2. So that's this right here. So we know this. And what we're asked to find, let's get another color, is negative 3 to 0. This is what we're asked to find. So how can we go ahead and set up the relationship as an equation involving definite integrals? Let me give you a moment to think about this, see if anyone could figure out the answer based off of that setup. Well, while you do that, I'm going to take attendance, then we'll go over it. Right today? I don't think she's missed at all. Not missing her. Anyone think they know? You looked at me wrong. Do you think you know?
Yeah.
What do you think?
6.
We have a 6 up here. Anyone else get a 6? 6 is the correct answer. Very good. Let's go over it. So the thing that we want to be aware of, and maybe I'll just use some colors to help us understand this. We know that the green here is going to be equal to the orange plus the red, if we were kind of thinking about this in terms of the intervals. So, of course, what we want to actually do is maybe solve this for orange. So we could think about this as that the orange is actually equal to, what would it be? The green minus the red? The green minus the red. So with that in mind, I'm going to go ahead and translate this to the definite integrals. So the interval from negative 3 to 0 of f of x dx, we don't know, that's what we're asked to find, but we know it's going to be equal to the integral from negative 3 to 2 of f of x dx minus the area obtained from the integral from 0 to 2 of f of x dx. And of course, because we were given the green was, 5, and then the red was -1. So we know that our answer here is just going to be 6. Very good. But this is an illustration of the rule number, this is rule D above. So this right here is rule D above. That you can add areas give under the curve of the same function. Any questions on that one? Okay. So let's see what some other rules what we have right here. So this right here looks pretty nasty, but it's just because we're not used to dealing with theta. So notice here, that we're looking at d theta. So this, our variable here is going to be theta. So we're going to consider negative pi to pi of g of theta. Oh, let's see. We're given that. Now, instead of writing that, I'm going to just go ahead and just write this over here. So this is what we're asked to find. So let's go ahead and I'm going to just rewrite this down here before I start applying the rules. So we have negative 3 times g of theta plus pi times h of theta. And then the variable, again, the d theta is just telling us that our variable of integration. So we have a couple rules here. The first one is that this negative 3 can be pulled out in front of the definite integral. So we have then g of theta, and then we're just going to evaluate that. Granted, we were already given this, I hope, yeah, right here. So notice that we just used the constant multiple rule to bring that out in front, and then we're using the sum addition rule to go ahead and continue to write. This is just going to be pi, because remember pi is a constant, from negative pi to pi of h of theta d theta. And then we have this right here is just that right there. So the integral here is going to be negative 3 times pi over 4 plus pi times square root of 2, or negative 3 pi over 4 plus pi rad 2. Pi rad makes me always think of pirate. Or matey. Give me that treasure. Okay. Come on, only 2 more weeks. I'm out of jokes at this point. Any questions on the properties here? All right. Now let's look at the next one, which is the nastiest function that I could think of right here to throw at y'all. Anyone think they know the answer here? If you do, turn to your neighbor and ask them if they know the answer. And some of you are thinking, it's like, man, my classmates are show-offs. But, Emma, I think I saw you first. What did you look at when you were trying to answer this one? The interval from 4 to 4. What do we know about this interval? How much width does it have? So the integral right here is going to be equal to 0. I mean, come on, you all know I'm not that mean. Anyway, so this right here, again, is the 0 width, what did we call it? The 0 width interval. Yep, so that was rule A up here above. So it's a 0 width interval, which is going to be rule A. So, any questions on those rules for definite integrals? Okay, so let's go ahead and look at the next page. So the integral formulas, there are more than 150 integral formulas located at the back of the textbook. Here are some common formulas. Okay, let me say this. You have to memorize these, but you shouldn't have to. Because I'm hoping that you're noticing, and we'll look at this in the next section, that if we looked at the integral, and I just want to kind of plant a seed right here, if we were to just consider the indefinite integral of x squared, let's say, x dx, this is going to be 1/2 x squared dx, or if you were to consider, well, not dx, plus c. Or if you were to consider the indefinite integral of x squared dx, this is going to be 1/3 times x cubed. Or if you were going to look at let's say we had some constant dx. Oh, don't forget the plus c there. Does anyone remember what the antiderivative of the constant is? Maybe just make this 1, make it more obvious. It would just be 1x, or just x plus c. So hopefully you're noticing, or I want you to kind of notice right here, these are showing up kind of as formulas here. X to the 1. So I will not provide these formulas, but they're just antiderivatives. And we'll explore more of that idea of why it's b minus a in the next chapter. For now, we'll just kind of look at them in terms of formulas. So we'll understand how to derive these soon, but let's look at some examples first. So if we were to look at this one right here, this is the first formula. What we're going to need to do, let me change up my color here. The formula is just going to be the constant, so it's going to be 7 times 6 minus 2, which is 7 times 4, or 28. That's all. But just to make sure we're okay with what are we actually looking at, what geometric shape is formed with the constant function 7? It's a rectangle. So if we were to actually go ahead and just sketch the graph of f of x equal to 7, 1, 2, 3, 4, 5, 6, 7, this is the constant function. If we were to consider 1, 2, from 2, 3, 4, 5, 6, 7 to 7, oops, that didn't work. So notice right here, this area, well, is 28. Just want to box it in there. It's pretty now. So, any questions on that one? All right, let's go ahead and consider number 9. If we were to consider notice this is using the second formula here, right here. So the answer is going to be 1/2 times 8 squared minus 3 squared, which is 1/2 times 64 minus 9, which is going to give you 55 divided by 3. Again, you can actually compute that directly just using the shape that is formed from this function. Anyone know what shape would be formed if we were using the identity function? You should try it. A triangle, yeah. Well, technically, it would be a trapezoid here, I guess. If you were doing it from 0, so just to see, what is this 55 over 3? If you were just to go ahead and sketch the identity function, 1 over x, it looks like that. And we're considering 1, 2, 3 to 8, 4, 5, 6, 7, 8. So this, I guess, would be more trapezoidal. I guess I tried to trap you with that question. But yeah, sorry. What's up, Weston? Why is it over? Oh, it should be over 2. That should be over 2. Good catch. Thanks. Which also follows from the trapezoid area formula. Any questions on that one? Okay. So the last one is a general, we're saying from 0 to b. So let's go ahead and set this up. See how this is worded. Use the definite integral to find the area of the region between the curve y equal to 10x squared and the x-axis on the interval from 0 to b. And b is just one of those things that could be 10. It could technically even be negative if you wanted, but then you could use other tricks to switch the interval. We'll talk about that more later. So really, this question's asking us to consider the definite integral from 0 to b of 10x squared. Remember that the 10 is a constant multiple, so we could pull that out and just consider from 0 to b of x squared. Oh, I should be careful here. This is the dx is important. You will, whenever you have an integral, you will always have the differential there, or the dx, or the d of whatever your variable is. It's indicating what is your variable. So we have the formula above. It's going to be 1/3 times b cubed minus 0 cubed, which is just going to be b cubed. Oh man, I keep making little mistakes. Don't forget this 10 needs to come along. So that would be 10 times b cubed over 3 or 10b cubed over 3. But again, all of this is a conversation about area under the curve. Any questions on these three examples? Okay, so now that we have some ideas in play, let's make sure that we continue to kind of emphasize the relationships between positive and negative areas. So if we look at number 11, we're asked to compute and interpret each integral in terms of area. So let's see. All right. Let me give you a moment to try 11, 12, and 13. Let me just give you a moment to try it. You may need to flip back to get the formula as maybe you're not comfortable with driving them yet, but let me give you a moment to try it. So the answers for 11, 12, and 13 are negative 16.5, negative 24.5, and then 8 respectively. How many got all of those? A couple of you, very good. Maybe just need a little more time. So let me go ahead and pull the graph in. I already wrote it earlier in my notes just to kind of keep it clear, and that's going to also show us what the top statements are about. So you can see right here, if you look at the interval from negative 7 to 4, that is this whole interval that I have this two triangles on. And you can see number 12 is from 0 to negative 7. So notice that whenever you get a negative answer, we're talking about area underneath the x-axis. But if we look at the 8 right here, you can see that's positive 8. That's the area of that triangle. And then also note, if you were to consider the whole area, this is again just the negative 24.5 that we got in number 12, and then is also going to be added to it the 8, which we got in number 13. So you can see that this is literally just the sum of areas. Of course, with the condition that area under the x-axis gives you a negative answer to your definite integral. Any questions on this one? Okay. So number 14, I kind of spoiled for you a little bit earlier. Does anyone know what the shape of that graph would be, the square root of 16 minus x squared? Semicircle. Many of you caught that. So again, we don't necessarily have a formula. Well, we have ways to get a formula for this. This one, it would involve something known as U substitution, and it's something you'll explore more in Calculus 2. But I think there's a few questions in the homework that literally just ask you, to evaluate the definite integral, considering it as the area under the curve. So this, let's try and get a decent looking semicircle. Sure, decent enough. So of course, radius is going to be 4. So the answer here is just going to be the region, the area under the curve, which would be pi times 4 squared divided by 2, because it's a semicircle. So this is going to be 16 pi divided by 2, or 8 pi? Yeah. So today has been a lot about understanding the definite integral as area under the curve. Anyone have any questions? Okay. Then I think we got one more page in this lesson. Yeah. So this idea we already talked about in section 5.1, the average value of a function. But before we had considered it as estimates using rectangles. But once you have the definite integral, you can just say the area is equal to that, because you just let the rectangles go to infinitely small, or there's infinitely many rectangles, however you're thinking about it. So this is really just the same formula we had earlier, but instead of going from like k equal like 1 to n of like some function, we're just using it as the definite integral. So remember the average, you add up the rectangles, which that does, and then you divide it by the width of the interval. That's all this formula is saying. Just adding up the rectangles, there's infinitely many, so we call it the definite integral with the idea of limits, and divide by the width of the interval. So find the average value of this function right here. So just kind of setting it up, the average of this function, and this is just the notation they're using, AV of f, the average of that function, is going to be 1 over 2 minus a minus 2. This is b minus a. And that's a is b given to us there. And we're going to evaluate that from minus 2 to 2. And it's going to be the square root of 4 minus x squared dx. So this is going to be 1/4 times, and well, this whole thing right here, we can just, while we don't have the formula for it, we do know it as the area of a semicircle. So it is going to be, let's make sure we do this right. So semicircle is going to be pi, radius is going to be 2 squared, and then we divide it by 2 because it's a semicircle. So this is 1/4 times 2 pi, which is ultimately just a phone call apparently, sorry about that, pi over 2. Is everyone okay with where we got that? And again, what is this? This is just going to be this value right here, because you could imagine like I don't know, you can imagine like something kind of push, like you have a water bottle, you push it up, the water in the middle goes up, and then it pulls it from right here. It's not like new water was added. So the average value is just going to give you some y value. And that would be if this water were to all level out to some sort of like rectangle, that would be the height of that rectangle. So it also makes sense if you just kind of think about the larger values pulling it up in the middle and things like that. Any questions on that formula? Okay. Let me give you 16 to try. See if you're able to apply that formula with the formulas from the previous page. And then that wraps up the section 5.3. And we will definitely do 5.4 tomorrow. Definite? Okay. So there's the setup of the formula. 1 over b minus a times the integral from positive 3 to 6 of x squared dx. So this is going to be 1 over 3 times, this will be the, let me color code this. This part right here is going to be 1/3 times 6 cubed minus 3 cubed. So this will then be 1/9 times 36 minus, oh, no, not 36. That's, I did that ahead of a 216. I was thinking squares, not cubes, minus 27. Simplifying this, you end up with 189 over 9, which is 21. So there is how you find the average value of the function from 3 to 6. I would encourage you maybe just to visualize the quadratic function right here from 3 to 6 and look at how that plays out. Ooh, that is sloppy. Anyone have any questions? All right. Destiny, question. Yeah.
So I wanted to know why we would not just take the formula where it's x squared dx where it's 1/3. Like, why do we have to do the 1 over b minus a first?
Sure. So the question is, why are we using this?
Yeah.
Because on these questions, we were asked to compute the integral.
Oh, okay.
That we're not asked for the average value of the function. So that is strictly the area under the curve. If you were to ask for the average value of the function, you consider the area, and then you divide it or multiply by the fraction, the width of the interval. That will tell you the average. Same principle with discrete numbers. You add together and then you divide by how much you have. So it's in the question. Hey, any other questions? Have a great day, everyone.